Yeah, I'm Miran, and actually I'm one of the inventor of CKK scheme, and um, I did as Stan introduced, I had a lot of experience with various privacy preserving applications with FHE, and today I want to talk about one of the recent work related to secure transformer inference. Oh yeah. This work was already presented at CCS 2025, and this is a joint work with Yang Hao and Dongwu and Xiaochen. AI is impacting our society in many positive ways, positive ways, but there are several privacy concerns because we should provide our data to use personalized service, such as Google Gemini, Meta Llama, and OpenAI, ChatGPT, and etc. And we don't know how this data is used. We don't know how this data is used in the future, and a lot of cases of data misuse. For example, Italy, they fined OpenAI for GPT's violation in collecting users' personal data. So lots of different misuse of private data once it was collected. It could be sold and it could be used that we don't intend. So our question is that, can prediction as a service be made trustworthy and efficient? So this concept is called privacy preserving personalized service. So there are so many X as a service, software as a service, function as a service, and kind of platform as a service. Let's start with the simplest use case. The client encrypts the data and sends only the encrypted data to the service provider. And the service provider applies the model to the encrypted data and sends the encrypted results. Then the client decrypts the message and read the predicted results. Unfortunately, traditional encryption protects only storage and transmission, not the computation phase. And HE, homomorphic encryption, enables computations to be performed without encrypting the data. So that's why it is considered as one of the promising solutions for the privacy preserving personalized service. Actually, they were the blog post from JAMA, and yeah, they expect, oh, this is bold. Yeah, they expect that have end-to-end encrypted AI within 5 years. And I think this work is the first to provide encrypted AI on a kind of a large transformer model. In particular, in our work, we focus on the transformer-based model inference here. What is transformer? Most of you heard about that. Actually, it's the self-attention-based architecture, where it was presented at 2018. And actually, it computes how strongly each token is related to every other token. So that's why it is called self-attention here. So it becomes the foundation of modern natural language programming models such as BART, GPT-T5, and BART. And the main advantage of these models is that the computation can be parallelizable. Let me explain it a little bit more. This model is composed of the stack of layers, and it consists of multi-head attention followed multi-head attention, and followed by two residual connection here, and normalizations, and with feed-forward in between. And multi-head attention allows the model to gather information from different perspectives, and it can be done by applying multiple and smaller attention head in parallel, kind of linear projection. And then the attention score between kind of two tokens from the key, the curry and key, is computed using a similarity measure between the as follows here, kind of using softmax and multiply again with the value vector. So as you can see, the most commonly used operation in this mechanism is matrix multiplication. Now, let's dig into matrix computation here. Let me skip what is FHE. It becomes boring. Yeah. FHE offers lots of flexibility in parameter selection, such as plain text model and vector size and polynomial degree, and ciphertext packing. And to improve performance, ciphertext packing technique is usually used. What it means that each ciphertext encrypts multiple plaintext elements and perform ciphertext computation in a synced manner. However, even with a fixed parameter set, determining how to put each data element in the ciphertext requires very, very careful design to achieve optimal efficiency. So let me introduce two representative ciphertext packing technique here. One is just encode slot, and the other is encode coefficient. So the first slot encode use DFTs like algorithm to transform a plaintext vector into an element of a cyclotomic ring, and it BGB, BFB, SKK scheme, they usually use such slot encoding. It supports vectorized operations in a similar manner, as I mentioned, kind of entry-wise addition, multiplication, and rotation, kind of moving values between slots. And it computes the same function on inputs at the same price of one computation, so it provides better amortized size and timing. And the other encoding method is coefficient encoding here. So encode plaintext values directly as an element of a cyclotomic ring. So few and TFHE, and definitely BGB, BFE, SKK scheme. The other scheme, we can also think about its coefficient encoding. So our question is that how to efficiently perform matrix computation over encrypted data, so especially matrix multiplication. So there are two approaches. One is inside FHE, just use the slot encoding here and just express matrix multiplication HE friendly. So what I mean, matrix is transformed into one-dimensional vector because that's only what we can support. And matrix operation is expressed as a composite of vectorized operations. And actually, there are several related works. One is depending on how to encode matrix, row major, and column major, and diagonal major. Column major is kind of one matrix is plain text and the other matrix is ciphertext. So it's a little, it's kind of not related to the actual general matrix multiplication. And diagonal major, however, their method, they focus on matrix and vector multiplication. So it's a little bit different from our final task, final goal. And the other approach is the one that has been investigated more recently, kind of outside FHE. So it usually uses coefficient encoding, and it uses reduction from encrypted matrix multiplication to plaintext matrix multiplication here. So what I mean, multiply matrix directly on the decryption equation. So it enables regular matrix computation optimization. So there are several related recent work, 2024, last year, 25. So let me explain a little bit more about two different approaches, inside and outside FHE approaches. I'm focused on row major matrix encoding method, which was presented at 2018. So we identify D-square matrix into just one-dimensional vector. Oh, and for simplicity, just assume that the slot size is greater than the matrix size. Kind of D-square is less than S. And we just use row major. So what I mean, just row-wise, kind of first row and the second row and then the third row, just row-wise. And the difficult part is that how to express the matrix computation into one-dimensional vector. So the matrix addition is straightforward, kind of, just the addition of two matrices is just corresponding to this component-wise addition between the vectorized A and B. But multiplication is more challenging. Actually the product of A, B, the corresponding vector, is expressed as the linear combination between linear combination of the permitted matrices of A and B, and each of them are multiply each other. So I think in our paper we show that this equation is true for arbitrary matrix A and B. And fortunately, this computation was kind of easy to implement. What I mean, given the vectorized A and B, then we first apply linear transformation to this vectorized input, and then the other permitted matrices are computed as the column shift from A or row shift from B. So that's why it's easy to implement. But there are several limitations to apply this approach to our secure transformer inference, because the small matrix size assumption here, but we need large scale matrix multiplication here. But you can say that just apply blockwise computation, kind of split the large matrix into smaller block and just apply the blockwise computation. But from our calculation, this way is not optimal. And actually, this approach is originally proposed for CCMM, but I mean, two matrices are encrypted. So it's not optimal for plaintext ciphertext multiplication, PCMM. So in some cases, AI or BI can be provided in clear text. So we need another solution. And matrix transposition, it also takes non-trivial because of the complexity. So there are several limitations to apply this row major matrix approach to the LLM. But outside FHE, for example, ring LW ciphertext of plaintext polynomial is corresponding to plaintext vector of messages 1D vector. So here, A and B, they are kind of the ciphertext of this message. And then we can extend this idea, we can extend this representation to multiple ring LW ciphertexts. So what I mean, just put more and more sample and more ciphertext to A and to B. And now the right side, the result of decryption will be the 2D matrix. So A times S plus B is M in the decryption equation. Then if we want to multiply W to the message M, then just multiply W to both sides, to the left and to the right. Then it means that A, B are ciphertexts, then WA, WB, they are the corresponding matrix, corresponding ciphertext for W times M. So we can just apply, that's why we can just apply the regular matrix optimizations for WA, WB, but they are another limitation here. So it is optimal when the number of matrices is n, right? We need n rows for kind of the compact packing. And the other limitation is that it needs a conversion to slot encoded ciphertext when performing coefficient-wise operations, such as nonlinear function evaluation. So it is kind of a non-trivial transformation to support such computation. And that's why in our work, we focus on the first and inside FHE approach to avoid unnecessary conversion. Now it's time to introduce our recent matrix multiplication, homomorphic matrix computation approach. Our idea starts from another new type of HE-friendly matrix representation. First, let me talk about the diagonal major matrix encoding. Actually, this encoding method was originally presented at Halabian Soup. So they are the main diagonal here, U0, and the super diagonal U1, kind of the next upper diagonal, and the second super diagonal U2, and the last super diagonal U3. So in their paper, there was some note that if an input matrix is provided in plaintext, or we can process it before the multiplication, then the best solution is to put it diagonal order, which would let us use the parallel systolic multiplication algorithm. So what it means that I think, yeah, if you study FHE, then you see, you definitely you definitely know this equation here. So A is matrix and V is vector, kind of input vector here, and W will be the output vector. So matrix vector multiplication. And the output W is expressed as the linear combination of the upper diagonal UI and the rotated vector of V. So it can be performed in a systolic array here. So multiply between diagonal and rotated vector, and then just accumulate and then pass data to the neighbor, kind of the upper to the next U1 is U0 U1 and UD minus 1. And okay, now actually our idea is kind of the extension of their diagonal measure matrix encoding. We can also think about another way of diagonal, kind of lower diagonal here. So the main diagonal is the same for lower diagonal, and the sub-diagonal L1 and the next sub-diagonal here and the last sub-diagonal here. So here, so one is upper and the other is lower. And by this definition, the first, U0, L0, they are kind of the main diagonal of this matrix. So they are the same. And interestingly, there are some relationship between the upper and lower diagonals. For example, the last lower diagonal L3 can be obtained by the rotation of U1 by 3 positions. And the same for the L2, but with a different rotation, kind of row 2. And the last L1 will be rotated by just 1 from upper diagonal. And there are more interesting properties here. For example, the lower diagonal of A is exactly the upper diagonal of transposed A. So actually we use these properties in the evaluation of secure transformer. So this is the main idea of matrix multiplication here. For simplicity, yeah, I used the script to denote row of matrix and superscript to denote the column here. And let's start with how to generate the first lower diagonal of C. Here C is the product of AB. So the first entry, C00, is the inner product of A0 and B0, right? So I put A0. Oh, so here our goal is to generate the lower diagonal of C, the 0th lower diagonal of C, the right side. Here, the highlight yellow. And so I spread the entries of A0 to the left for A, and B0 to the right for B here. Let's put it. So it's trivial, right? And how about C11, the next entry here? So this entry is the inner product between A1 and B1, and the first row of A and the first column of B. And by the isometric property of the rotation operation, it can be expressed as the inner product between rotated A1, rotated B1. So let's put it here. It's rotated A1 here. I put it here, and rotated B1. And the same for the next C22 here. And by some, but the C22 is the inner product between the A2, B2, but rotated row square here. So I put it here, row square A2 and row square B2. And we almost there here. Okay, the last one. Okay. Then so as you can see, using 4 vectors for A and 4 vectors for B, then multiply each other and then add, then we have the first, the 0th lower diagonal for C. And surprisingly, actually this is my intention, the diagonals for A corresponds to upper diagonals of A, and the right side for B, it's corresponding to exactly the lower diagonal for B. So it means that the lower diagonal of C, one lower diagonal of C can be expressed, can be computed using just upper of A and lower for B. And we can also extend the same idea for the first lower diagonal L1 for C. But a little bit different is that the same for B, kind of lower diagonals for B, but upper diagonals, but it needs rotation here. And then multiply, kind of the same computation structure here, multiply each other, and then add, then we have the first lower diagonal. So more generally, if we are given square matrices A, B, then the rth lower diagonal of the product can be obtained as follows here. So the expression is so simple, right? So for A, we need the upper diagonals, but some rotation here. And for B, we need lower diagonals here. And just multiply each other and then just accumulate here as needed. So in the context of H computation here, so if PCMM, what it means if the lower diagonal, only the lower diagonal for B is encrypted, then it can express as the linear aggregation and plain text multiplication between the rotated A, rotated upper diagonal of A, and the encryption of lower diagonal for B. And the CCMM, when both are encrypted, then this kind of the same, just multiplication here, but we need rotation on encrypted data here. So it's very easy to implement, and it kind of optimized for both PCMM and CCMM. And matrix transposition is kind of for free, but a different format, right? So if we are given the matrix, if we are given the lower diagonal, then it's definitely it just corresponds to the upper diagonal of A transpose, right? And we usually assume that the ciphertexts are provided in lower diagonal. So and inputs, the outputs, they have kind of the same format, lower diagonal. So we provide unified encrypted matrix representation, and it can be reusable for subsequent computations here. And it easily extended to parallel matrix multiplication, as we usually do, kind of interlace multiple matrices, and that's the computation here. And it's easy to extend to the square matrix multiplication to generate various size. So it's kind of a good exercise. For example, this is non-square matrix multiplication here. And kind of, yeah, A is rectangular and A is tall and B is fat. Yeah, then kind of the same upper, lower than the main diagonal for C, and the rotated here for upper diagonals, and rotated here for the upper diagonals by 2 and by 3. And actually there are, so some cases is that just the slot size is the same as the diagonal size and the dimension of matrix. Then just put each diagonal to just vector the slot. But if sometimes the slot size is greater than the matrix size, for example, suppose that the slot size 8, then maybe we can put 2 different matrices together, kind of A and B. But in some case, slot size is much greater than the matrix dimension and the number of the matrices to be computed in parallel. Then in that case, we define another parameter which is called diagonal packing capacity. So what it means, we pack multiple diagonals together. For example, this case, S is 16, S is 16, then just put a different diagonals for A, B, kind of L0, L1, that'll be the first diagonals for A and B together. And the next one, the L1, AB, it's kind of concatenation of L2 and L3. And we batch the ciphertext computation using this packing capacity here. Actually, in our experiment for the secure transformer inference, the slot size 2G15 and H, the parallel matrices, that'll be exactly the number of multiple heads in transformer here, and S is 16. So it is kind of fixed if we choose one model here. And the dimension size, the matrix dimension size 237. So it means that we can put 2 to 4 different diagonals in one ciphertext. So we if we use this packing capacity method, then we maximize the slot uses. Let me just skip it here. And so it's time to apply our matrix multiplication to secure transformer inference. Some are trivial, but some are non-trivial here. For the PCMM, for example, the linear projection or feed forward, we can just apply our previous our method to this to the evaluation of this operation. But sometimes it needs it requires so many CCMM, and when we try to optimize our solution, we focus on the CCMM. So suppose that we want to multiply this type of matrices A and B and C. So from our proposed way. So actually, just see the output the C matrix. Then we have the main diagonal here, L0, and the other, the next lower diagonal, L1. And by just our founding, it can be expressed as the upper diagonal and lower diagonal here. And yeah, just linear combination here. And as I mentioned, in our application, in the secure transformer inference, we use the diagonal packing capacity, for example, C16, right? So we can pack multiple diagonals into one ciphertext. So that's why we need to optimize this idea, the basic matrix multiplication to apply to the real problem here. For example, suppose the L0, L1, the lower diagonals for B, they are provided into one slot. Then the first, okay, so the corresponding U0 maybe and row U0, that'll be expressed, that'll be contained in the same slots, right? Same slots here. And just put the other way, just put it here, just write. And then we can have L0, 1 together. But as you can see, the same diagonal, for each, so for B, it is okay. So just suppose that the L0B, L1B, they are the one ciphertext is provided in advance as input. But how about A, the upper diagonal? So one slot in one ciphertext, the same diagonal are provided, the same diagonal are packed in one slot. So, and as you can see, it rotated differently. For example, U0, but row U0, and U1, but row to the cube U1, and row squared, and row to the 3, row to the 2, just row, and it's kind of messy, right? So it needs around n times n rotation here, and it's just to transform kind of, if we, for example, if we are given matrix, we are given ciphertext of U0, U1, then we need non-trivial transformation to generate the ugly rotated upper diagonals for A. And in total, it requires n+1 n rotations to support matrix multiplication here for A, B. So our idea is that just change the mind here. So originally it was, so we just changed, we just changed the matrix encoding way. For example, suppose that we are given the replicated diagonals for B. Then, okay. Then if you see the details, then yeah, if you see the details in our paper, then you can easily the difference from what should be filled out into this slots, the corresponding slots. So here it'll be need to change here and change here, change as follows here. So just change the encoding way of B, encoding for B, then the corresponding upper diagonals for A, that'll be, oh yeah, U1, U0, U1, yeah. And we can use the following facts. U0 of A is the same for L0 of A, and U1 for A is the rotated L1 of A. So it means that now it becomes kind of, yeah, a more better way. For example, just L0, L1, L1, L0, but rotated by 1 for each one, rotated by 1, and rotated square, and rotated cube. So it means that its ciphertext of A contains different lower diagonals, kind of L0, L1 together, but rotated by the same amount. So just by changing this representation, then it requires 2 times m times n over c, and here c is the diagonal packing size here. And we also, and in our paper, we also propose the optimizations based on BSGS. So yeah, we rotate the ciphertext of A internally, right? We need to apply the internal rotation, but kind of we rotate them at the first and just multiply each other and apply, and we need some masking operation and apply only a single rotation to the some intermediate result, and then just add. Then by this BSGS integrated way, then we can reduce the rotation by half, from the previous LL approach. So in conclusion, the UL, the straightforward applications of our matrix multiplication, it requires n times n, but kind of different LL approach, then it becomes kind of 2 times mn over c, kind of smaller than before. And we can also we can achieve 2 times faster, speed up by applying BSGS. So by comparing between the row major and our diagonal major, so we provide kind of parallel large-scale matrix multiplication, and our method is kind of more efficient for PCMM, I think. And in terms of transposition, the row major way requires non-trivial computation overhead, but our work is kind of for free. So when we calculate the required key switching operation, I think, then we show kind of 9 reduction over the row major way. Oh, and actually there is one more advantage of our method, of our diagonal method. If the upper diagonal of S are provided, the upper diagonal means the lower diagonals of S transpose, then each row of S is distributed across the same position in different slots. So what I mean, most cases, we need row-wise computation on the matrix. For example, row-wise addition here. And suppose that we are provided the encryptions of lower diagonals of S transpose. This is exactly the upper diagonals here. U0, okay. Oh, U1, U2, U3. And by our definition, each row of S is distributed across the same position in different slots as S0 and row S1, row square S2, row to the cube S square. So if we want to apply F row-wise on S, for example, apply F on S0, S01, S02, S03, or S22, S23, S20, 21, and that's the second row or the third row and the first row. So they are kind of placed in different slots here, different ciphertexts. So just apply F to the different ciphertexts, and no computation is needed between slots. So what it means that our diagonal major encoding method and its corresponding matrix multiplication, matrix representation is very friendly to row-wise computation over row-wise computation. Okay, let me just skip it here. Go to the, yeah. So we apply our method to transform-based inference here. So as you can see, the input is tokenized input. It's encrypted here, and then there are several PCMM, and from our kind of perspective, that what it means, the lower diagonal of S transpose and lower diagonal of transpose input are just proposed. So lower diagonal of X transpose here, X is input here, and they are provided here, and then PCMM here, kind of the multi-head attention here, and then kind of CCMM to compute the the attention score and the softmax, and then again CCMM again, and and then layer normalizations and kind of feed forward for PCMM with W1 and W2 here, and then apply this computation by L times. And then finally pooling, hyperbolic tangent, and classification. And finally, we got the encrypted output here. So this is the experiment result. So we focus on BERT-based model, which consists of 12 layers, and the parameter size is 100 million, and the token size is 128. That corresponds to the matrix dimension. And from our implementation, it took about 10 minutes with only 0.8% accuracy drop. And compared to the recent the SOTA Nexus, that it took about 2.7 hours, and we achieved 60 times improvement here. Oh, and I didn't talk about that I didn't talk about the non-linear evaluation strategies, but in our paper we did we did another kind of optimizations to do that, kind of softmax, and so if you are interested in this way, in that, then please check and please see our paper. Oh, and interestingly, even after even applying the several optimizations, algorithm optimizations for matrix computation, linear algebra, and nonlinear computation, linear evaluation. But as you can see, bootstrapping accounts for 50% in runtime. So let me conclude my talk. In our paper, we propose new efficient parallel matrix computation based on diagonal major encoding, and I didn't talk, but we also think about another optimizations, kind of blockwise PCNM, and we integrate the SGS method to optimize CCMM. And another benefit of our method is that we just apply the row-wise computation for free without conversion here. But I think that there are much room for optimization here. For example, in terms of level. So in 2018, the row major encoding method, it requires 3 levels. And in our work, it requires 2 levels here. So we save 1 level, right? 1 level. But actually, we need replication string CCMM. So, and it, to generally replicate raw diagonals, and it requires 1 level, and actually it requires a few rotations. So, I think that that's why maybe there's some more nice idea to optimize our matrix multiplication algorithm, I think. And our implementation is publicly available at GitHub. And actually, there are several future works such that in our paper, we just focus on low latency, but I think sometimes high throughput batch processing is also needed. And in our paper, we started, and we need to extend secure inference to much larger parameter LLMs here. And also, the interesting task is that privacy preserving training for large language models. And I think there are several works about that. And potential applications beyond LLM as that kind of genomic analysis, or and machine learning, kind of neural network, or transfer learning. And actually, there are so many problems that needs us. So this is the end of my talk, and I'm happy to take any question here.